Hello and welcome to my video on displacement, velocity, and acceleration compared to distance and speed. So we're looking at all the different types of graphs that are related to these different topics, these scalar and vector quantities. All right, here is a situation. We're going to draw all possible graphs of the above scenario, and hopefully by drawing all the graphs, we're going to get some idea of what the graphs can possibly mean. We'll talk about it afterwards, but if you pause the video right now, try your best to draw this, and then press play when you're ready. All right, we're going to take a look at these different graphs. Hopefully you had a chance to draw out the different graphs, but basically we're all going to be in the positive direction, so we can actually start with all of them being positive, although maybe not quite so wonky, Mr. Drager. Okay, so all of them are going to have time on the bottom. So this is our x-axis. All of them are going to have time on the x-axis. Okay, and so I'm going to just read out our question, and then we can actually just get started right away. For our scenario, I guess. Here we have distance, which should have meters. Time, I guess, should be in seconds. This is speed, so let's put speed in, no, we're going to have that in seconds too. Velocity in seconds. No, not seconds. What am I talking about? Speed in meters per second. Over here, we're going to have displacement in meters. Velocity in meters per second. And acceleration in meters per second squared. Okay, Mr. Drager was stopped at a red light in his old Toyota Camry. Glancing to the left, he saw a fiery red Ferrari. Watching the light carefully, green! Mr. Drager slammed on the gas, speeding through the intersection, only to be stopped by the next light in a matter of seconds. At least I beat the Ferrari. Oh wait, he was turning. So draw all possible graphs of the above scenario. So let's break it down into the different parts here. Okay? So we're stopped at a red light. So that's the first key part. We're stopped at a red light. So at the beginning, the distance is 0. Okay? So distance, not moving. Okay? Not moving. And so watching carefully, I'm not moving so that the speed is also 0. But what we're watching carefully until the light turns green. So maybe not moving for a while, and then the light turns green. So then I'm going to start to accelerate until I see the stop sign, and then I'm going to slow down. Or the stop light, and then I'm going to slow down. Okay? And I'll be stuck there too. So at some point, so maybe there's a couple points here. So I slam on the gas, I accelerate. That's the second point. Until I see the next light. Okay, and then I slow down and stop. And then at that point, I'm stopped at the next light. So maybe I'll just do that in different colors so we can tell. So these are different points in our story. Okay, if we're talking about speed, we're at a standstill at the beginning. Okay, and then it accelerates the speed in a straight line until the point at which basically I have to slam on the brakes, in which case it comes right back down, and then it goes straight across to the end. So this is the exact type of question that you could be given, and see how we changed it from distance to speed, just qualitatively. No numbers, we just changed 5 different points from distance to speed. Okay, when we're talking about displacement, velocity, and acceleration, we would have a slightly different thing going on. So let's take a look here. Okay, let's take a look. If we are basically, well, it's going to be very similar, okay, at first, where our displacement is going to look very similar because the whole time we're going in the positive direction. So, whoops, I don't know what happened there. But the whole time we're going in the positive direction, right? So our displacement is positive the whole way, okay? But if I turned around and went back, this would start going back down, but not in this case. Okay, velocity, also very similar. It would go like this, like this, like this. But because we now have a velocity and a displacement graph, we can actually do an acceleration graph. Okay, and this is important. So acceleration is 0, and then the acceleration is whatever it is, positive, right? And then at that point, at whatever point that is, I press on the brakes, goes negative, and then it's back to that, back to 0 when I'm at a standstill. So those are a couple different graphs. Let's talk about maybe a different possible situation. So maybe a better situation to talk about is another displacement versus time graph. Displacement, and maybe we'll go in kilometers. If you remember in the last video, I believe it was the last one, no, 2 videos ago, I talked about how it takes me about 16.9 kilometers to get to and from work. That is a distance, okay? But in terms of displacement, I actually go somewhere around 8 kilometers of displacement. So what's going to happen here is I'm going to go, I don't know exactly the correct amount of stopping, but it's going to be something like this, where it kind of stops, goes up, and then it kind of stops at a stop sign, up, stops, whatever, till it reaches that point, whatever point that is. Then it's going to go down until I get back home, right? It's going to look something like that. Now, it can go back down because it is a displacement. Whereas the distance graph over here would look more like this. Going up and then keep going up. It would look like that. It would look very much different than before. Here, if we have a velocity versus time graph, now we can compare the velocity. So in this part, it is mostly up here, and then over here it goes to the negative because I'm going the opposite direction. It's hard to do these little bumps, so maybe we'll just do a straight line, ignoring the fact that there are stop signs and whatnot. Okay, and last but not least, we have our acceleration. So an acceleration graph would look, well, kind of like ours did before. Okay, where we have well, if it's a straight line, actually it'll be a 0. Right? And an instant drop, but anyway. Okay, I hope that this video helps you understand displacement, velocity, and acceleration a little bit better. I know they can be confusing, but basically you just have to get used to trying to switch between them. There are a few things to look for in these graphs, okay? So let's just back up a little bit. There are a few things to look for in these graphs. Let's erase some stuff and do some more simple graphs. It's not erasing for some reason. Okay, I'm not sure why that is. Let me delete it then. Click on it and delete it. What? Okay, well, I'm gonna draw I'm gonna draw the line beside that. Okay, ignore this. Okay, we've got displacement versus time. Okay, if you look at this graph and we find the slope of the line, which we can get by looking at rise over run. Okay, this is the slope of the line, is rise over run. That is the same thing as saying the change in distance or displacement over the change in time. And guess what that is? The velocity. So the slope is velocity. Slope equals velocity. Okay, this is beautiful. Slope of displacement equals velocity. Slope of distance equals speed. Okay, slope equals speed. Whereas over here, slope equals velocity. If we have a velocity versus time graph, let's just go like that, then the slope here is something else. Slope is, again, rise over run, or in this case, change in velocity over the change in time, which is acceleration. So slope equals acceleration in this graph. Acceleration. Okay, what's also cool is that if you take the area under the line, right, whatever that area is, in this case it's a triangle, so the area equals base times width divided by 2, but if you take the area under the line, then you get base is time, the change in time, times by the velocity divided by 2. And this is actually our displacement. So the area equals displacement. So there are a few really cool ones here. Slope is velocity, slope is acceleration, slope is speed, and importantly, area is displacement. If acceleration has a legible line of some sort, if it has a line that's actually possible to read, like this, then you can actually do a similar sort of thing, where you get the area for acceleration, right? So area equals, and in this case, just because it's a rectangle, it's length times width, which in this case would be the change in time times the acceleration, which is the velocity. So in this case, the area equals velocity. So those are some of the different things that you need to know about when we're talking about graphs, especially these movement graphs in Science 10. We need to know the slopes, what they mean. We need to know the areas, what they mean. And these are the ones that matter. I hope this video helps you understand acceleration, displacement, and velocity a little bit better, and maybe a little bit of the scalar, distance, and speed as well. Good luck!